Let's dive straight into this, shall we? Picture this. You're sitting in the exam hall. The clock is relentlessly ticking down. You open your Cambridge physics pass paper, specifically looking at syllabus code 0625, and right there staring back at you is a massive, multi-part question on momentum, impulse, and the conservation of momentum. This is a notoriously tricky area. Now, I want you to look at two hypothetical students taking this exact exam. First, we have Alex. Alex is a walking textbook. When Alex sees a momentum question, they just word vomit every single physics fact they've ever memorized onto the page, hoping something sticks. There's zero analysis. Then we have Sam. Sam is the speed demon. Sam rushes through the paper, completely misses the crucial command words in the prompt, and throws down a final numerical answer without showing any logical steps. The heartbreaking part? Both Alex and Sam actually know the underlying material, but when the results come out, they both hit a massive wall. Their marks simply do not reflect their knowledge. Today, in this explainer, we are going to tear down their flawed answers, look at the red pen marks side by side, and figure out exactly how to avoid their mistakes together. Whether you are tackling the core 0625 syllabus, the combined and coordinated sciences like 0651 or 0652, or even stepping up to O-Level 554 and AS Level 9702, the strategy we are about to unpack is completely universal. So I have a very serious question for you. What actually separates a B from an A star in physics? It's the ultimate frustration, isn't it? The dreaded grade plateau. You study for hours on end, you know all the definitions by heart, you can recite the textbook backward, but no matter how many past papers you do, you just cannot break past that B grade boundary. It drives students crazy. But here's the brutal truth. Raw, memorized facts are absolutely not enough to secure top marks in Cambridge exams. Alex and Sam both know the basic definition of momentum, but neither of them is getting that A star. Why? Because the difference lies entirely in how your answer is designed. I want you to stop thinking like a student and start thinking like a master architect. Think of it like building a skyscraper from the ground up. Every single paragraph, every mathematical step, every unit must be a structural masterpiece. The top-tier student doesn't just list facts. They demonstrate a deeply connected conceptual understanding that effortlessly transfers to completely unfamiliar contexts. They build a logical bridge from the first principle to the final conclusion, and they make it impossible for the examiner to take marks away. Look at this quote right here. This comes directly from a senior Cambridge examiner. They stated, "The difference often comes down to how well you understand terminology and structure." We are going to frame this entire explainer through the eyes of that examiner. Put yourself in their shoes for a second. It's late at night, they are marking their 400th paper, and they are tired. They do not want to hunt through a messy paragraph to find your hidden points. They want to be guided through a highly logical, structured reasoning process. They are actively looking for analytical depth that goes far beyond superficial breadth. If we want to impress them, if we want to steal every single available mark, we absolutely have to speak their language. We need to use the right terminology, the appropriate mathematical formats, and a structural approach that leaves absolutely no doubt about the physics concepts at play. You are not just writing an answer. You are presenting an undeniable argument. Okay, so here is our structured roadmap for this explainer, so you know exactly how we are going to build your exam mastery step by step today. First, we'll quickly ground ourselves in the core momentum principles. Second, we will reveal the procedural solving framework. This is the real secret sauce. Third, we'll spend some time decoding examiner insights. And finally, we will dive into the vault of avoiding classic exam mistakes. Let's get to work.
Section 1, Core Momentum Principles. Let's set the foundation.
Let's start with the absolute basic building block. Momentum, which we denote by the lowercase letter p, is defined as mass multiplied by velocity. The equation is beautifully simple. P equals mv. But listen to me carefully. The trap here is not the equation itself. It is how we use it under pressure. Velocity is a vector quantity, which means direction absolutely matters. It is literally half the definition. Imagine a 2-kilogram tennis ball flying and hitting a wall at 5 meters per second, and then bouncing straight back at 3 meters per second. The velocity has changed from a positive 5 to a negative 3. The mass stays the same, but the momentum completely reverses direction. If you're like our friend Alex, you might just blindly plug the numbers into P equals mv, calculate a difference of 2, and move on. But by completely forgetting to define your positive and negative directions, you've already lost the method mark before you've even finished the sentence. Top candidates always explicitly assign a positive direction in their margins before touching their calculator. And that vector concept builds directly into our next critical principle, impulse. Impulse is defined as a force multiplied by the time it acts. But here is the critical analytical leap that separates the good students from the great ones. Impulse is also exactly equal to the change in momentum. So impulse equals F times delta t, which also equals delta mv. Think about a real-world car crash. If a car slams into a rigid, unbreakable concrete wall, the entire change in momentum happens in a fraction of a millisecond, an incredibly tiny delta t. Because that time factor is so incredibly small, the force must be absolutely massive to achieve that same necessary change in momentum. This is exactly why modern cars have crumple zones designed into their front ends. The crumple zone physically crushes, which increases the total time of the collision. By stretching out that delta t, it dramatically decreases the resultant force experienced by the passengers inside. This specific mathematical relationship between force, time, and momentum is tested every single year without fail. Which brings us to a massive sticking point: resultant force. According to strict Cambridge guidelines, resultant force is defined as the change in momentum per unit time. F equals delta P over delta T. Why do so many hardworking candidates find this specific distinction so hard? Because they constantly confuse impulse with resultant force. Listen closely. Impulse is the total overall change in momentum. Resultant force is the rate at which that momentum changes. It is a subtle but absolutely vital difference in terminology. If an exam question asks you to calculate the force exerted by a cricket bat on a ball, you first need to find the total change in momentum of the ball, and then you must divide it by the milliseconds the bat was actually in physical contact with it. Lacking this precise terminology in your written explanation means leaving method marks on the table. And hey, before we continue building this strategy, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Finally, for our core theoretical principles, we have the undisputed law of conservation of momentum. The rule states that in a closed system, the total momentum before an event is exactly equal to the total momentum after the event. For your IGCSE exams, we generally only need to worry about this applying in one dimension. We are talking about objects moving in straight lines, crashing head-on into each other, or exploding apart from a standstill. A classic exam scenario they love to use is two ice skaters pushing off each other from rest. Before the push, neither is moving, so the total momentum is a big fat zero. After the push, one skater glides to the left with negative momentum and the other glides to the right with positive momentum. When you add their two new momentums together, they perfectly cancel each other out to equal exactly zero. You must solidify this rule in your brain. Total initial momentum equals total final momentum. Always write that statement down first. Section 2, the procedural solving framework. This is where we turn theory into undeniable marks. We are now completely shifting our focus from pure physics theory to the method mark strategy. Remember, Cambridge examiners actively award points for the logical process of your problem solving, sometimes even if your final arithmetic on the calculator is slightly off. Let's walk through the 4-step procedural framework that practically guarantees a well-structured response. Step 1, deconstruct the command word. Does the question say state, describe, or explain? Explain requires you to provide underlying physics principles, not just describe what you see happening. Step 2, extract relevant data. Take your pen and write all knowns and unknowns in the margins. Make them visible. Step 3, select your analytical framework. Is this an impulse question or a conservation question? Write the blank formula down immediately on the page. Step 4, execute and present. Plug in the numbers, solve it, and present your answer with the correct terminology, the right significant figures, and proper units. This is the physics success blueprint. Following this architectural process builds an absolute immunity to dropping silly marks. If you watch Alex and Sam rewrite their answers using this framework, you literally see the examiner's red marks transforming into green check marks. Okay, let's do a quick interactive workshop challenge right now. I'm putting a metaphorical 60-second timer on the clock. Imagine a highly complex data table on your screen showing different masses, varying velocities, and collision times. In a real exam, you do not have 10 minutes to leisurely read through it. The specific data interpretation skills required here are all about speed and accuracy under intense pressure. Your brain needs to instantly scan, extract the core trend, and interpret the relationship. For example, you need to visually scan and spot that as the mass of the object doubles, the change in velocity perfectly halves for a given constant impulse. Once you extract that trend, you use it to draw an evidence-based conclusion. Visual scanning of complex physics data sources to find these hidden relationships is an absolute must-have skill for the A-star boundary. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGSC to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acexams_IGSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3, Decoding Examiner Insights. Let's get inside the head of the person marking your paper.
We are now looking at exactly what higher-order assessment objectives demand from you. It's time for Challenge 2, Find the Flaw. Let's compare a weak, purely descriptive approach against the rigorous, evaluative thinking that earns the highest marks. Look at our rushing student, Sam. Sam writes this paragraph. The car hits the wall and stops. The crumple zone makes it safer because it absorbs the crash. Okay, audience, spot the flaw. What is losing marks here? Time's up. The flaw is that it is entirely descriptive. It's superficial breadth. There is absolutely zero physics terminology, no mention of resultant force, no mention of collision time, and no mention of momentum. That earns 0 marks on a 3-mark question. Now look at an evaluative, A-star architectural answer. It says, the crumple zone physically increases the total time of the collision. Because the total change in momentum remains constant, an increase in time results in a proportionately smaller resultant force on the passengers, governed by the equation F equals delta P over delta T. Boom. It is structured, it is evidence-based, and it justifies the physics with hard evidence.
What if the exam throws a curveball and asks you to compare 2 completely different crash scenarios? This brings us to Challenge 3, Speed Writing. You have a 30-second mental timer right now. Comparative analysis in momentum requires a very specific mechanical structure. I highly recommend using the Peel framework, point, evidence, explanation, link. We must identify similarities and differences using comparative connectives, like whereas, conversely, or in contrast. Let's say vehicle A has twice the mass but exactly half the velocity of vehicle B. Compare their momentums using Peel. Point. They have the exact same momentum. Evidence. Mass times 0.5 velocity mathematically equals 0.5 mass times velocity. Explanation. Because momentum is the direct product of mass and velocity, these inverse proportional changes perfectly cancel each other out. Link. Therefore, both vehicles would require the exact same impulse to bring them to a complete stop. Do you see how powerful that is? That is how you engineer a flawless paragraph under pressure.
Section 4, Avoiding Classic Exam Mistakes. Let's open up the examiner's vault.
Let's emphasize the ultimate examiner alert. Notice how these 2 approaches contrast starkly on your screen. On the left, we have generic, memorized textbook definitions. On the right, we have answers specifically engineered to the context given in the prompt. The most classic, heartbreaking mistake you can make is memorizing a brilliant textbook paragraph and just pasting it blindly into the answer box, completely ignoring what the specific scenario actually is. If the exam scenario is clearly about a rocket launching into the vacuum of space and your written answer starts describing ice skaters pushing off each other because that's the example you memorized, you are going to lose heavy marks. The examiner desperately wants to see your theoretical foundation applied directly to the real-world, highly specific scenario they just gave you. Every single point you make must intrinsically link back to their given context. Let's recap the top 3 mistakes pulled straight from the official principal examiner reports, so you know exactly what to double-check in your final minutes. This ties into our complete answering system. Number 1, answers are often way too vague. Writing, the force changes is terrible. Writing, the resultant force decreases due to a proportionally longer collision time is masterful. Number 2, students completely forget to check their format and presentation. This means omitting the standard units, using the wrong amount of significant figures, or, worst of all, not showing you're working out. Number 3, as we just hammered home, answers are not specific to the given context. This is where you deploy the final part of our system, the time management matrix. Allocate your time based strictly on the marks available. A 4-mark explain question needs 4 distinct contextualized Peel points. Don't spend 5 minutes on a 1-mark recall question. Structure your time as rigorously as you structure your answers. If you find yourself panicking and struggling to remember the core differences between momentum, impulse, and resultant force under the harsh fluorescent lights of the exam hall, I want you to use a memory hack, the visual story method. Instead of recalling abstract letters on a page, encode these physics concepts into a vivid, moving narrative. Picture a heavy, shiny bowling ball rolling aggressively down a wooden lane. That heavy movement, that is your momentum. Suddenly, it violently smashes into the pins. The exact time the ball is physically touching the pin, multiplied by the raw impact force of that hit, that is your impulse. And that impulse is what causes the resting pin's momentum to violently and suddenly change direction. Visualizing the physical scenario as an active, dramatic story practically forces your brain to understand the deep relationships between the variables, guaranteeing you recall the formulas accurately when it counts the most. Listen to me. The social proof on this is undeniable. Students who actually implement these architectural physics strategies, who decode the command words, who religiously apply the Peel framework, and who utilize the time management matrix, see an average improvement of 2 entire grade boundaries. They go from struggling at a C to comfortably sitting at an A. But that transformation only happens if they practice consistently with our weekly explainer breakdowns. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acexams_IGCSE and click that bell. Don't let another exam pass you by while you're stuck making the same structural mistakes.
And this brings us to the end, leaving you with one final provocative challenge. How exactly will you apply this architectural blueprint to your very next physics past paper? Are you going to keep dumping raw facts onto the page like Alex? Are you going to rush and ignore the command words like Sam? Or are you finally going to step up and build an evaluative, undeniable masterpiece? The structure, and ultimately your final grade, is entirely in your hands. Drop a comment below right now with your specific target grade for physics and the single biggest topic challenge you're currently facing. Our expert team responds to every single comment to help you out. Like and share this video with a study partner who needs a wake-up call. Ace the Exams. Your Cambridge success starts here.